But let's first talk about Japan. Again, I'll move pretty quickly through this, so feel free to circle back to it later if you want to. Here's a tsunami coming over the retainment wall in Japan. And probably many of you have seen pictures or seen footage of, if you haven't, if you go to YouTube and just Google tsunami or just search for tsunami, there's a very large number of videos from cell phones and stuff of this. And it was the 2011, magnitude 9. Shaking lasted for up to 6 minutes, and in some places measured almost 3 Gs of peak ground acceleration. An extremely large peak ground acceleration measured in some places. And 6 minutes of shaking. So another thing I want to stress is that when we talk about peak ground acceleration, that's one measure, but that doesn't tell you the total amount of energy that's released. It's also the length of time of the shaking is a big factor as well. So peak ground acceleration is one very important measure. That's a measure of how much stress your system was, whatever your substation or your building or whatever was subjected to. But another is the length of time that it was subjected to that. So to do 3 Gs for 6 minutes is very, very large. 6 minutes of shaking is a tremendously long time for shaking. Okay. About 15,000 people dead, or maybe almost 20,000 once you account for missing and things like that. And then the tsunami, this tsunami, as it flowed inland and just washed all this stuff away, moved at about 15 miles an hour, which honestly is faster than most people. So some athletes maybe can keep up with that, but most people aren't going to be able to run 15 miles an hour very fast.
That's a 4-minute mile.
Okay, yeah. So it's you're not going to outrun it, right? If you're in the area.
Good head start.
Yeah. It's just a wall of wet debris, wall of wet, muddy, churning debris, right? So your chances of surviving that are very, if you're caught in it, are very, very small. Another thing I mentioned is that we mentioned that, interestingly, talking about the Cascadia Subduction Zone maybe activating other earthquakes. Another interesting thing, though, is that, so that's activation of other earthquakes in space, spatially, right? But then the Cascadia Subduction Zone also activates other earthquakes in time, temporarily, because you have the main one, and then there's aftershocks that hit as well. So you're not just getting the magnitude 9 Cascadia Subduction Zone. You're also getting some aftershocks that are going to come after that. And the aftershocks themselves can be very big earthquakes. For example, for Japan, after their main earthquake, they had 5 magnitude 7 earthquakes, which are pretty big in amongst themselves, and 80 magnitude 6 earthquakes. So you're going to get aftershocks as well, and the aftershocks are pretty sizable, particularly for a Cascadia Subduction Zone. Okay, so looking at Japan, obviously they're along the Ring of Fire here. Okay. The Tohoku epicenter was right there in the 2011 earthquake. Here's a map of that tsunami propagation. You can't, here you can kind of see it. See that little reddish? Yeah, like you were saying, it kind of funneling that over there. I'm not quite sure what's bathymetrically is going on there, but tends to be a little stronger right there. But anyway, you can see this tsunami energy being propagated across the entire ocean. Just some pictures of the complete just debris and damage, destruction. I've somehow parked that boat on top of that building. Fires, not able to do anything about that. Right, just a oily, yucky mess. Talk a little bit about the Japanese grid. Japanese grid is 60/50 hertz system. This is 50 hertz on the north and 60 hertz on the south. It was developed that way because there was 2 separate grids developed at the same time, and one was using 50 hertz equipment, one was using 60 hertz equipment. And eventually, when it was time to connect them together, it was easier to connect those together at conversion stations rather than to have one switch completely over to 50 hertz or vice versa. So a little bit of an interesting system. We're going to focus, though, on this utility, which is TOPO, which is the Tohoku electric utility, and TEPCO, which is the Tokyo. So we're going to focus on these 2 utilities right here. Because remember, the earthquake was right here. So we're going to focus on the damage in those. Sorry, it's a little bit small, but here's Japan on here. This just shows, again, please look at this after the fact, but it shows anyway where all the power plants are in Japan. And what's shown here is, this is all thermal and nuke plants. So along the coast, it's all primarily natural gas, and these green ones are nuke plants. So it's primarily thermal and nuke along the coast. Those are the systems that were threatened by the earthquake and the tsunami. The Tohoku Power Electric Company, again, coming back to this, that's this one right here. And this one's Tokyo, so Tohoku, Tokyo. Tohoku is about 18 gigawatts of capacity. Tokyo obviously is larger. It's 39 plus 9 plus 17 plus 5. It's somewhere around 70-ish or so gigawatts. So about 18 gigawatts for Tohoku, about 70 gigawatts for TEPCO in terms of capacity. One interesting thing that I want to keep stressing with the Japanese earthquake is that There was some seismic damage, but they were pretty well prepared for that. Most of the damage was due to the tsunami. In Japan, most of the damage was the tsunami damage. Okay. So for Tohoku, that was the northern utility, right after the earthquake, they lost about 12 out of 20 of their power stations shut down. So they dropped about 55% of their capacity right after the earthquake. And the damage is primarily caused by shifting things off their foundation, damage to coal loaders and things like that. Right? So they lost about half of their capacity right after the earthquake. For Tokyo, the Tokyo Power Electric Company, they lost about 30% of their capacity right after the earthquake. Right? So the shaking shut down about 30% of their capacity. So one lost about 50%, the other lost about 30%. The big one, of course, that people talk about is Fukushima. It's very well known. So that was in the TEPCO system. And what happened there then is the plant shut down due to the shaking, but then the tsunami damaged one of the generators that are responsible for running the cooling system. So they lost their backup generators due to the tsunami. So they couldn't run their cooling system. And without the cooling system, then they had 3 meltdowns. They had meltdowns in 3 units. It's estimated that the management of that campus will have to go on for several decades, just continuing to manage that facility until things cool down enough where you can deal with it. Interesting to try and deal with that. One thing that they were worried about was seawater getting in underneath the plant and so you get contamination of the seawater, the radioactive material underneath the plant. So actually what they tried to do is they actually tried to build an ice wall in the ground around the campus. So actually drilled down and inserted cooling elements and refrigeration system and froze the ground. That's like crazy like movie Hollywood stuff. It's amazing to me that they did that, but they did that, right, to make this ice wall that contains the groundwater underneath. However, that was deemed to not be effective. So they think that failed. And so now they kind of really don't know what to do about the contamination with the water table. But anyway, looking at decades of management for that. There's an excellent report, again, it's in the reference here. There's an excellent report on this that was published in IEEE Power and Energy Society magazine from a couple years ago. I'll put that on the course website as well. Let me make a note of that. But that has a very, very nice history of that whole breakdown. We looked at, one of the things that we looked at for this project was impact on renewable energy systems. Obviously for solar systems, if they're PV and they're on structures, if the structure fails, then it's most likely that the PV system has failed. For wind turbines, though, none of Japan's wind turbines failed. They had capacity about 2.3 gigawatts and none of them failed. Wind turbines are pretty seismically resilient. They're actually made to be quite bendy anyway. They actually deflect about 10 feet at the top. So if you're in the nacelle of a wind turbine on a windy day, you really feel it. Because the tower, it's almost a 100-meter tall tower, and it's actually quite bendable. So they have good seismic capabilities. So it's just an interesting side note that did well. They had permanent loss of generation, but it was offset a little bit by the fact that a bunch of the load got wiped out. So post-earthquake, in their recovery, they had some loss of generation, but a bunch of the load and the tsunami just completely wiped out these communities, and so that load is gone. So in a way, some of the loss of generation was offset a little bit by the fact that you had a loss of load. So for example, in the summer of 2011, this is a couple months after the earthquake, right? TEPCO and the Tokyo Power Electric Company still had about 10 gigawatts that hadn't come online yet. And Tohoku, a power company, still had about 1 gigawatt that had not come online yet, right? But that was offset a little bit by the fact that the load had been lost. One of the key points that the tsunami did most of the damage primarily to the load, to the distribution system. Very widespread damage to distribution poles and things like that. And again, kind of reiterating this, what you're looking at for recovery times. 90% restoration in 6 days, 95 in 10 days. For Tokyo, 90% in 4 days, 95 in 7 days. Right? So those are what organizations that were really well prepared, that's what they could do. And here's what that recovery. Here's homes without power. So here the earthquake happened, boom, here's 4.5 million homes without power. And then they recovered that down to only a couple 100,000 after 10 days. Right? And then here was an aftershock. It lost a bunch more in the aftershock. Yeah? And then again recovered that really quickly in just a couple days. They were back again. So I'll bring this up at the end of the short course. We're going to talk about how we can quantify resilience. You can use curves like this to quantify resilience. Basically, the area under this curve tells you something about the resilience of that system. So this will come up again later.
Do you know what the percentage of the total homes was?
You mean this 4.5 million out of the homes? No, I don't. I don't know the total load. It would have been, no, I don't. I'm not sure. Let me try and find it, though.
Maybe we could allow it, if we had enough like that, we could allow us maybe to estimate what percentage of our load might go out and how quickly.
Yeah, that's an excellent question. Where?
Second block, third block down, right? It's just the number out.
Maximum number of homes with no supply, 4 million. Yeah, so it's just pointing out that number. Yeah, I'll try and get that number for you, though. Liquefaction damage was very large in Japan. They have a lot of liquefiable soil as well. One interesting thing to note, though, is that the countermeasures against liquefaction worked well. So that was a data point that if you take efforts to treat liquefiable soil, that might be worth your time and money. Right? This was one data point that where countermeasures had been taken, that it worked well. Japan's resilience, they have that early warning system that we talked about. I'm very good on that. They get hit with earthquakes all the time, so they're very prepared. Their building codes are very stringent. They have some seawalls built up as well for tsunami inundation. This is actually an ongoing, very controversial topic in Japan because the seawalls are obviously very unattractive. Right? You're building a high concrete wall. However, the government kind of likes it because it's a big public works project and there's a whole bunch of jobs generated. So there's a push and pull right now in Japan on whether we should build more of these walls. And they're very well prepared. They have excellent plans for dealing with resilience. Moving on to Chile in 2010. So this earthquake right here in Maule, Chile, 2010. Magnitude 8.8. This one is casualties are lower on this one compared to Japan, certainly only about 500 people. But 4 minutes, 0.65 G peak ground acceleration. Compare that to Tohoku where it's 6 minutes and 3. Right? So not quite as strong as that, but still quite severe. Hundreds of thousands of homes destroyed. Here's the tsunami propagation. So the earthquake was over here, and here's the tsunami propagation, just to show that energy going across the ocean. So a tsunami generated here as well. Right? Just some pictures of things destroyed. Again, similar to the Japan picture, right? Just debris, stuff everywhere. One thing you see, distribution poles tilted. One thing I'll come back to here when you talk about Christchurch as well is that this is pretty typical of what you see post-earthquake in these communities. But in many cases, in some cases anyway, these can still operate. So one thing we'll come back to, and I'll mention this again when you talk about the Christchurch case, is that overhead lines actually do okay in earthquakes. That you can have some tilting of these poles, but still have the system be functional or still be repairable at least somewhat easily. And I'll show some pictures of that in the Christchurch earthquake.
I was just wondering about it, just giving a quick Google because a lot of our news infrastructure is underground.
Yes, and I'll talk about that. There's a big threat there.
It seems like that'd be more susceptible to earthquakes, less susceptible to other things on regional trees and stuff like that.
Yeah. Yeah, spoiler alert. So just a couple slides, I'll talk about that. Yep. For Chile, the transmission system, they recovered that in just a few hours, so pretty quick recovery on that. One interesting thing to note, though, is that the transmission system, obviously Chile is a long, skinny country, right? So you have a north-south oriented system. They actually brought that up in 2 islands and then connected it together later, which is an interesting example of a system that was brought up islanded and then reconnected. The distribution system was very severely damaged. They also have a lot of stringent building codes because they're regularly subjected to earthquakes. So they know what's going on with earthquakes and they build to it. After the 2010 earthquake, though, they have evacuation drills, very, very active. They think that the drills and things that they implemented post 2010 were very important in a 2014 earthquake, magnitude 8. And so it just says some lives saved during that. So I think that was. They also have an early warning system there as well, some sirens and things like that. So the New Zealand case, this is the last of the case studies. I'm moving through these kind of quick, but this is the last of them, and this comes to the buried cable question. So here's New Zealand, right, and here's Christchurch. There's actually a fault that runs right through here. There's Christchurch right there. There was 3 of them. And so this is also an excellent paper. This is an earthquake spectra. It's by Alexis Kwasinski, who's a colleague of mine, or at least I know him a little bit. But this particular paper, if you look up this reference, is one of the best journal papers I've seen on summarizing the impacts of earthquake with regard to the electrical system. So 3 earthquakes in 2010, 2011, and 2011. some of the New Zealand utilities that were affected, but I'll skip that. The earthquake was here, here, and here. You see right on top of Christchurch. Here's the spectra of the earthquake, and you'll see this again more when Leon gives his talk, but just an interesting example that they actually gave this in the journal paper. And what's shown here is the amount of acceleration. What's shown here is acceleration on this axis, and this is period on this axis. And this is the resonant period of your structure. So in other words, what this tells you is that if you had a structure that had a resonant period of 0.1 seconds, you might have seen something like 1.2 Gs of acceleration of that structure. Right here, for example, if you had a structure that looks to be about 0.2 or 0.3 seconds resonant period, you might have had about 1.6 Gs on that particular earthquake. So just I want to talk a little bit about metrics, and Leon will show some more about this, but that's one way that you can quantify the strength of an earthquake, is this kind of response spectra, which shows you sort of what the expected response of a structure would be if subjected to that earthquake. Here's just some pictures of some damage. Here's a capacitor voltage transformer that's used for instrumentation. See, it's broken off there. These types of things, and again, Leon will talk about this, but these types of things, these types of structures that you tend to see in substation yards, these tall, thin structures made of ceramic, it's not great, not great seismic properties, right? And so these kind of bushing-like things that are tall and skinny, obviously, are going to be subjected to high seismic stresses and bending moments. Here's landslides. We talked about the damage of landslides. Here's a transformer room, and the landslide just came in, destroyed all that. So not necessarily damaged by the shaking directly, but damaged by the land that was knocked loose in the shaking. Liquefaction. Here's very, very liquefiable soils in Christchurch. So here's areas of liquefaction, and then here's infrastructure damage plotted. You can see that very much correlates. Liquefaction causes lots of problems. Here's some pictures. Here's a sand boil. Author standing in that. Here's a tower that's settled into the sand. Then one of the major outcomes of this, coming back to your point, is buried cables. So they had a fair number of buried cables in Christchurch. The buried cables did not do well. They did not do well in liquefiable soils. So in other words, if you have buried cables do well if the soil's not liquefiable. If the soil is liquefiable, though, it will spread and shift and it will shear the cables. And that's what they saw in Christchurch. So one of the key outcomes for this, that's a particular relevance to a lot of people in this room that deal with power systems, is that buried cables in liquefiable soil don't do well. And buried cables have excellent resilience characteristics in many, many, many ways, but one of them is not when the ground is shifting around them. Then they tend to shear. And so they had, for example, all 80 11 kV underground cables had faults that were buried cables in liquefiable soil. Underground cables, it takes longer to locate it and repair it. So that's another factor. We think about the prepare, absorb, recovery. The recovery part of it is going to be longer for the buried cables. Right? Harder to go find the faults, harder to go fix them. Okay? So a key outcome of this, as I just said, a key outcome was that should avoid the use of underground cables as much as possible in liquefiable soil. So that's not anti-buried cables. Buried cables are great. But buried cables in liquefiable soil are bad news when there's earthquakes. Okay? That was one of the key outcomes of this.
So by the same thing with the water pipes?
Yes. Yes. And yeah, anything that's in the liquefiable soil is going to shift and get pushed around. That's right. Yeah. So here's an example of an overhead line. So here's an overhead line that's tipped. So this is tipped, but they came and they just dropped a big concrete block here to keep it from falling over. And but then this can continue to be used. Right? That looks like some repairs necessary, but they propped it up and they come back and you can put cables up there and then you use it until you can come back and finish the fix later. So this is just another data point that we see in a lot of these cases, that the overhead lines can take damage, but their repair is generally quicker, certainly than it is for the underground lines. Right? So I don't mean to sound like I'm for or against one or the other, but that's just a data point that's seen. It's one of the things that is good for overhead lines. Just some other pictures here. So you can see this big fault line here. A transmission tower right here, and there's a big crack in the land. So here the big lateral spreading, so the land is actually moved. You can see the insulators are being pulled. So the tower moved underneath it. There's stress on that. Here's a guy wire connection that's all bent over and buckled. A transformer sitting on its pads that's settled and shifted, so the pad underneath settled in the soil and tilted. One big outcome they had also from this Christchurch paper was they had a whole bunch of transformers that tripped offline because they have mercury switches that detect tipping. And so those got activated in the seismic shaking and tripped offline. So it's something that they didn't anticipate. They didn't think that they were going to have a bunch of these mercury. They didn't even think of these mercury switches causing problems. But these switches kept tripping when there was shaking and tipping. Another really thing I like about this paper is that it's one of the few resources that actually talks about how much money was spent and how much money could be saved. Okay? They spent, prior to the earthquake, they spent around $6 million, New Zealand dollars, in preparation. So beforehand, they prepared. Primarily what they did is they reinforced unreinforced masonry buildings. So they went to like substation housing rooms and things like that and reinforced those rooms. They estimate that they might have saved something like $30 to $50 million because of that effort. Right? So it's one of the very few resources I found where they actually talk about a cost-benefit analysis. And you can see it's not trivial. They spent $6 million, but they probably saved 30 or 50. Right? So obviously, is that applicable to us? I don't know. It depends on a more detailed analysis. But it is one data point where that was very helpful for them. I mentioned the mercury-filled switches tripping, and that was a problem. Also, backup diesel generators played a really key role in their recovery. They used quite a lot of those and deployed them quite liberally. So that's a data point that's something that we should consider in our systems, is having backup generators ready, particularly mobile units. One of the utilities experienced damage to their administrative building and wasn't able to operate it, so just a data point as well that it's good to have backup operations buildings. And another really nice key point is that for one of the utilities, their newer equipment, higher voltage equipment, that was designed to substantively meet the IEEE 693 standard, which Leanne will talk about in the second half of the thing today, fared very well. So that equipment that was designed to do well in seismic conditions did do well. Right? So just a data point that hopefully those standards are meaningful, and that testing and that qualification is useful and actually performs in the real system. And then just some final costs, and just as a point of interest, for how much these events cost, these 3 earthquakes. So you're looking at repair costs for these utilities that were in the range of millions of dollars for this, just so a data point kind of get a sense for how big these events were and how much money they were laying out. Any questions? So let me see where we are on time. I think maybe I caught up a little bit. A couple minutes over. Any questions or comments on any of that? Yes, Diane.
So I think one of the key themes that keeps emerging in my head is the fact that so many of the areas in Oregon will be islands, not just electrically, but because of bridge failures or landslides. I have a family member who lived in Pensacola about 10 years ago, and a pretty major hurricane came through there. And her house was still standing, but just a 4-foot storm surge came through. She said, imagine walking into your house and just draw a line 4 feet, and everything below that is covered in sewage. So all your drywall has to be pulled out, all of your kitchen cabinets. And they had to go to Michigan to get an RV for her to live in. And their whole neighborhood was questionably safe to live in because people were just, pulling out all this, really contaminated material from their homes themselves. There were no contractors that were available. And this is an area that would not be difficult. There were people coming from all around the country to help. But if we have, a real lack of ability to move resources, your discussion about debris and then, of course, thinking about how many trucks do we have available? Do we have fuel to run those trucks? What will be the pressing need in those communities? If you have a few trucks and they're available, is the first thing that we do going to be restoring the energy system? Or will those trucks be commandeered by some, emergency management system for other purposes? I don't have answers, but those are just some of the questions that I came to my mind as we were talking this morning.
So if you think about everything that I talked about, what were some of the key points there? One is that buried cables did not do well in liquefiable soil. I'm just kind of brainstorming some of the key things that I thought of. So
The soil matters.
You got to know what the soil is, right? You guys site-specific studies, right?
Geotech on the site.
Yeah, so you can get course information, but you need to do site-specific studies, right? Yeah. Another is that the economic trajectory of the community can be permanently changed. So even after you recover from the direct damage, if you don't do that quickly enough, right? You might permanently suffer after that.
I was actually really surprised by the 2 to 3 week range of restoration. So that stuck in my head as maybe a goal to shoot for.
Yeah,
You know,
right.
if those other folks under large impacts are able to do that, that could be at least something to throw at the board to shoot for.
Yeah.
Preparing.
Yeah, days to weeks range to shoot for in terms of recovery.
I guess the big thing that I keep thinking of ties to that is the amount of repair infrastructure that we have kind of available in order to completely restore the 7,000 transformers needing to be replaced. That's Northwest's supply of transformers. To get those around and have them in backup.
Yeah. And a data point that the pre-earthquake preparation was very economic, right? Spent $6 million and maybe saved almost 10 times that in the case of the Christchurch earthquake.
Probably means that utilities do not have anywhere near enough liquid fuel on hand to sustain their operations. In the absence of the bulk fuel.
Yeah, accessibility of liquid fuel, and you may, I think, will talk even more about that.
I know we have, underground tanks on site that we fill our trucks up with, but obviously that's not a good idea. You don't have a little gas station, but.
I think also just the necessity to coordinate with other types of utilities, whether it's water, wastewater.
Yeah.
Where are we all going to make places secure for people and then start consolidated?
Yeah, the interconnectedness of lifelines, right? It's not just one lifeline. Yeah.
I was struck by the presentation that we showed at Christchurch. Like every port. Yeah. Much of downtown Portland is back to
Yeah. Liquefiable soils and landslides are big threats.
Northwest of that, Pacific Portland. Everybody's sitting right here. So maybe outside of this area to help support.
That strikes me as part of the problem as well with landslide maps of Cascades. I'd be interested in drilling into that a little more versus, say, where the transmission lines are going through passes across the Cascades, because so much of your generating capacity is on the eastern side of the Cascades in the first place. If you have landslides in the single areas where you can actually get lines through, it's going to complicate things even further and restore power to that way it goes.
Yeah, that's a good point. I think one of the other key points is that the tsunami is as much of a threat as the shaking, as the earthquake.
Pile on, transmission lines across the Cascades, look at the transmission lines across the Coast Range and the lack of generation on the Oregon coast. So that's why the outlook for power restoration along the coast is so much longer in the number of months.
The other thing that nobody really talks about it, like the airport flying a levee system. There's a lot of things down by the river that are too low, and I don't know if anybody ever talks about those levees breaching and burying, inundating the airport, and a lot of those low-lying areas. If anybody steps out, the liquefaction of those levees. Yeah. The whole Marine Drive complex is routed all the way to the point. When they flooded, and then if the dams are going to potentially breach, they might be releasing large amounts of water in the river that was meant to run extremely high to save the dams. And if the levees are already breached or weakened, you can have a secondary catastrophe there. You can be able to use that part of it. It's like a huge amount of development, and all through the water, kind of like what happened in New Orleans. They were below sea level. They were asking for it. Well, we kind of are too.
I had a question about, you kind of mentioned a little bit along those lines, you mentioned dams failures, like Northwest and Oregon, 80-85% hydro or something like that. I don't know if there's any Army Corps people in here or anything, but is there a sense of how resilient the Columbia projects are? Yes. And how much that would get through this?
Yeah, it's an excellent question, and it's something that we looked into. There are some reports that have been done. There's some. Sorry, I didn't mention it in the presentation, so I'm glad that you brought it up. There are some reports that have looked at that, and the dam should do well. The dam should do well with regards to the seismic activity, with regards to the shaking. Not anticipated to have any failures of the dams due to that. However, there may be some risk due to underwater landslides. So you may have some dams, their penstocks and their intakes or their outtakes that could be obstructed by underwater landslides. So the dams themselves should be okay. That was one of the outcomes of our study, but there still could be some impacts.
One thing I'm wondering is like when you mentioned something like 3 Gs in a unit, like on the Columbia spinning 100, 200 RPM on the giant one, wiping bearings and rubbing stator windings out, and then it's 6 months to repair it, kind of thing. That even though the dam's standing, maybe we don't have power, for that reason, but I don't know.
Yeah.
The acceleration is lower than that far.
Yeah, true. The one last thing I would say, I want to make sure they kind of stay on schedule. So the one last thing I would say, the key outcome, or the thing I want people to take home is the prepare, absorb, recovery part of it. That all 3 of those are important for resilience. Or, if you don't have the financial resources to focus on one of those aspects, then maybe there's another aspect of that you could focus on, right? A resilient system will be good at any one of those 3 things or all 3 of those things.